The screen is visible, guys.
Yes, sir.
Okay. Today I'll discuss an important derivation, that is steady flow energy equation. Okay, already I discussed, but you have to understand this equation properly, and also the application of steady flow energy equation. Okay. Before that, so I'll recap what is first law of thermodynamics. Okay. Okay. First law of thermodynamics state that in a closed system, the amount of work transfer is directly proportional to the amount of heat transfer. Okay, so we can take the work into the system and heat from the system. Also, we can take the heat into the system and work from the system. Hence, the heat and work are two mutually convertible forms of the energy. Okay. And it is based upon the law of conservation of energy. Okay, so law of conservation of energy states that the energy neither created nor destroyed. The total energy associated with the system remains constant. That is the concept behind first law of thermodynamics. Okay. Now we are going to illustrate the first law of thermodynamics with Joule's experiment. Okay. So this is what you are seeing on the screen is the Joule's experiment. Okay. So it is having a closed adiabatic vessel consisting of the shaft with pulley and weight arrangement. Okay, the temperature in the system is represented by using a thermometer. We studied thermometer is a temperature measuring device. Okay, don't make confusion between temperature and heat. Temperature is a thermodynamic property. It gives the measure of degree of coldness or hotness of a body. On the other hand, heat is a form of the energy. It occurs by virtue of temperature difference. That is, one is heat and one is the temperature. And so, and we studied adiabatic vessel and uh, mm, another one is diathermic wall. Okay, adiabatic wall is the one which does not allow the flow of heat between system and surroundings. Diathermic wall is the one which permit the flow of heat between the system and surroundings. So this system, this is the Joule's experiment for first law of thermodynamics undergoing in a cyclic process. Okay, we studied thermodynamic process and a cyclic process. Cyclic process is the one in which the initial state and final states are identical. Okay, and thermodynamics process is the one which is in which the initial state and final state are not same. That is the thermodynamic process and the cyclic process. Here we are going to deal with the cyclic process. Okay, this is the PV diagram. So I'll explain how it's going to take. Okay, the first, so this is the arrangement. Here it is having the insulated container or adiabatic vessel, thermometer, it is a paddle wheel and it is a pulley, and the weight is connected to the pulley. Okay. Here, starting we are having like this. Okay. And initially, the thermodynamic system having the properties P1, V1, and T1, etc. Okay, and it is enclosed by a adiabatic wall, which does not permit the flow of heat. And here it is a paddle wheel, pulley, and this is the weight. Okay, and we studied thermodynamics definition of work and also the mechanics definition of the work. Okay, mechanics definition of the work is it is a product of force and displacement. So amount of the force is required to move a certain object for a particular distance. That is the mechanics definition of the work. But in case of thermodynamics, we are going to define it as the whatever the change in thermodynamic properties takes place, uh, uh, means either rising or falling of the weight due to the change in thermodynamic properties of the system. Okay, so that's why we explained where this with weight example. Okay? That is the thermodynamics definition of the work. Okay, so when we are going to down the weight, okay, by certain amount, okay, by means of the pulley, when the paddle wheel rotates inside the fluid, okay, then the pulley rotates and thereby falling the weight for a particular distance. Okay, start just you assume that starting you are having the distance weight somewhere here. Okay, so when the paddle wheel starts, okay, it rotates the pulley on the other hand, thereby causing the weight to move for a certain amount. Okay, we studied the work done on the system and work done by the system. The work done on the system is a negative quantity, and the work done by the system is positive quantity. On the other hand, Q, the heat transferred to the system is positive, and the heat rejected from the system is negative. Okay, so here. Starting all the fluid properties are represented by P1, V1, and T1. So when the paddle wheel rotates, okay, then the pulley rotates and thereby causing the weight to fall for a certain distance, and that is represented by certain distance dz. Next, okay, and here you see the xy coordinate diagram. So 1 to 2 is the work done on the system. Okay, so means work done on the system. To this is nothing but your stirrer work. Okay, so the work is done. We are considering this fluid enclosed in a closed vessel as a system. Hence, the work is done on the system. So you have to take in this direction. 1 to 2 is our the work done on the system. Okay, important. There is one is compression and one is the expansion process. So it is similar to our compression process. You have to start from here and end here. This is 2 to 1. Okay. Now what I'm going to do? I'm going to remove this adiabatic wall. Okay. Can anybody tell what happens? Okay, whenever you remove the adiabatic wall, what happens? So after removing the adiabatic wall, so that the system interacts with the surroundings. Okay, then the system and surroundings interact with each other and then attain a common equilibrium condition. Okay, so that there will be change in properties from P1, V1, T1 to P2, V2, T2. When you remove the adiabatic wall, there will be change in thermodynamic properties. Okay, and so this is represented by state 2. Okay, so whenever you remove the adiabatic wall, so that this system and surrounding it interact with each other and thereby attaining a common equilibrium condition. We studied thermal equilibrium, mechanical equilibrium, chemical equilibrium, and also thermodynamic equilibrium in first module, so that they interact with each other. After some time they attain a common equilibrium condition. Okay, and represented by properties 2 to 1. Okay, so thereby it interacts with the surroundings and then so it reaches the initial condition. So after some times, okay, it attains a common condition and then it reaches the initial state. Okay, after certain time, the both system and surroundings attain a common equilibrium condition. Okay, so there will be heat transfer as you remove the adiabatic wall, then there will be a transfer of the heat from the system to surroundings. That is represented by the curve 2 to 1 in xy coordinate diagram. Okay, and this is the diagram and this is the cyclic process. Okay, so it here the initial and final conditions are same. That is called as cyclic process. And remember, cyclic integral of any property is 0. Like cyclic integral of dq is 0, cyclic integral of dt is 0, cyclic integral of uh, ds is also 0, because the both internal energy and entropy are the property of the system. Hence, all cyclic integral of any property is 0. Okay, So 1 to 2 is the work done on the system. Starting we are having the pressure P1, V1 and T1, so that after performing the work on the system, it reaches to state 2, that is P2, V2 and T2, after removing the adiabatic wall, so that system interacts with the surroundings and thereby attains the common equilibrium condition, and that is represented by Q2 to 1. Hence, uh, there are two process executes a cycle, and here we can say that the work transfer is directly proportional to the heat transfer. Okay, so cyclic integral of dq is always proportional to the cyclic integral of d2. Okay, a statement is important whenever a system, that is closed system, you remember we are dealing with the closed system, not open system. So open system is nothing but our steady flow energy equation. Okay. Whenever a closed system is undergoing a cyclic process, then the net heat transfer to the system is directly proportional to the net work done by the system. Okay. And cyclic integral of dq is proportional to cyclic integral of dw, and the constant of proportionality, that is cyclic integral of dq equals to j into cyclic integral of dw. So a constant of proportionality j is called as the joules equivalent of heat. This is called as the first law of thermodynamics undergoing a cyclic process. Now next, you refer this diagram here. We are having a system thermodynamics. So you studied thermodynamic system in first module. Thermodynamic system is one in which our attention is uh, focused to analyze a problem. Okay, so whether it may be a particular space in the region or it may be the entire space in the region, that is called as thermodynamic system. So there are three types of thermodynamic system. One is a closed system, second one is open system, and third one is isolated system. In closed system, okay, the mass of the system remains constant. There will be only the energy transfer takes place between the heat and between system and surroundings. Okay, on the other hand, open system is one in which both mass transfer and energy transfer takes place between system and surroundings. And in case of isolated system, will be neither mass transfer nor work transfer takes place between system and surroundings. Okay, these are the three thermodynamic system. Okay, now let us consider the system where the heat is taken into the system and the work transfer by the system. Okay, whatever the net energy transfer is the q minus w, that will be stored inside the system. Okay, so one is the mm, Q is the heat input to the system, and W is the work transfer from the system. So net the energy transfer is given by Q minus of W, and the energy in storage is neither the heat energy nor work energy. Okay, remember, whatever the net energy accumulated within the system is neither heat energy nor work energy, and it is, we are calling it as the internal energy, or simply the energy of the system, and it is equals to, that is q minus of w, that is the net energy transfer is equals to the change in energy, that is a nothing but a delta E. The first law of thermodynamics. Remember, we used this formula in all the chapters. Okay, remember, it's one of important formula. Q minus W equals to delta E, or Q equals to delta E plus W. This internal energy is either represented by symbol E or sometimes U. Okay, both are used to represent internal energy. Okay, this is the first law of thermodynamics. You consider this diagram. So if there are more than one energy transfer quantities involved in the process, then how to write the first law of thermodynamics equation? You see, the Q1 is the heat taken from the system, and W1 is the work input to the system. Similarly, the Q2 is the heat input to the system, and W2 is the work output from the system, and Q3 is the heat input to the system, and W3 is the work output from the system, and W4 is the work input to the system, and Q4 is the work heat output from the system. Like that, if there are more than one energy transfer takes place in a system, then we can write. So you have to remember the sign convention for work transfer and heat transfer, and summation of the heat transfer equals to the summation of work transfer. Here you see Q1. Q1 is your negative. Okay, it's a minus Q1 because it is the heat rejected from the system, and the sign convention is negative. And then Q2 is the heat added to the system, that is minus Q1 plus Q2 and plus Q3. Okay, so you have to sum up all the heat transfer quantities, minus Q1 plus Q2 plus Q3 equals to W1. W1 is work done on the system. You have to take minus W1 plus W2 plus W3 minus W4. Okay, that's why you see the arrow mark. Suppose if work into the system, you have to take negative sign, and the work output from the system is positive. Okay, so minus Q1 plus Q2 plus Q3 equals to delta E plus W1, sorry, minus W1 plus W2 plus W3 minus W4 plus delta E. This is how to write the first law of thermodynamics equation. Okay. Now we'll prove, sometime they'll ask, prove that the internal energy is a property of the system. Okay, most of the time they used to ask, okay, we are having three things. Energy is a property of the system, and in the entropy chapter also we are proving the entropy is property of the system. So this is a diagram to illustrate the internal energy is a property of the system. Okay, energy or internal energy. You see the XY coordinate diagram. So this one is here, the 1 to 2 is a thermodynamic process following the path E. Okay. Now from 2 to 1, from state point 2 to state point 1, we are having the two paths. One is path B and one is path C. Hence we are having the three paths. So the thermodynamic process starts from initial state point 1, it reaches to state point 2 by following path A, and it returns from state point 2 to state point 1 by following path B, and also by following path C. Okay. So the diagram you have to draw whenever they ask, prove that internal energy is a property of the system. Okay, and here once again we can tell that it is a cyclic process because the initial and final states are identical. Okay, in thermodynamics, so concentrate more on PV diagrams, TS diagrams. Okay, so you have to draw this diagram by showing all paths and all state points. Now we have to apply the first law of thermodynamics. Okay. According to the first law of thermodynamics, the sum of heat transfer is equals to the summation of work transfer. Okay, that is represented by cyclic integral of dq. Cyclic integral means summation of heat transfer equals to cyclic integral of dw, that is summation of work transfer. Now you consider the cycle 1A to B1. Okay, so now I'm not considering the passy. Initially, I'm considering the cycle 1A to B1. Okay, this is a cyclic process, considering two paths A and B. So for the process 1A to B1, cyclic integral of dq, that is 1A to B1 equals to cyclic integral of dw. For the path 1A to B1, you have to mention the cyclic path. Okay, now we have to split the cyclic integral for the two paths A and B, that is integration of dq between the state points 1 to 2 for the following path A. So we have to split summation of heat transfer equals to summation of the work transfer as, that is integration of dq between the state point 1 to 2 by following path A plus integration of dq from the state point 2 to state point 1 by following path B. This is the summation of heat transfer by following path A and B. Okay. Equals to, similarly, you have to write for the work done also. That is integration of dW between the state points 1 to 2 for the following path A plus integration of 2 to 1 for the path B. Okay, you call it as equation number one. Okay, so first you have to write the first law of thermodynamics statement, and then you have to split the process. That is integration of 1 to 2, integration of dq for the process 1 to 2 for the following path E plus integration of dq from 2 to 1 by following path B equals to the integration of dw between the state points 1 to 2 by following path A plus integration of 2 to 1 by following B. Okay, so we call it as equation number 1 to B. Now we are going to consider this part. Okay, instead of B, we are going to consider path C. Okay, now you consider cycle 1A to C1. 1A to C1. Okay, then how we are going to write the first law of thermodynamics for this cycle is integration of dq in the state points 1 to 2 by following path A plus integration of dq for the path 2 to 1 by following path C. Okay, you see the second equation, integration of dq between the state points 1 to 2 by following path A plus integration of dq by following path 2 to 1 for the path C equals to, uh, you have to write the equation for the work transfer, that is integration of dw between the state points 1 to 2 by following path A plus integration of dw for the path 2 to 1 by following path C. Okay. So first you have to take cycle 1A to B1, write the first law of thermodynamics equation. Next you take 1A to C1, write the expression for first law of thermodynamics. So you call it as equation number 2. Now you have to compare equation number 1 and 2. Okay. So equation number 1 and 2 you compare. Okay. So here by comparing the equation number 1 and 2, we can tell that you see the first term and third term gets cancelled. Okay. So that here and second term we are going to equate, that is whatever the cyclic integral of dq between the path 2 to 1 equals to the cyclic integral of dq for the path C, so that after comparing the equation number 1 and 2 we can clearly tell that okay, the cyclic integral of dq for the path 2 to 1 by following the path is equals to the integration of dq between the state points 2 to 1 for the path C. Okay, and also you have to compare the RHS quantity as well. Okay, so this third term gets cancelled, so we can clearly tell that the integration of dW for the state points 2 to 1 path B equals to the integration of dW between the state points 2 to 1 by following path C. Okay. Hence, we can conclude that whatever path it may follow, the integration of dq is exactly equals to the another path. Okay, that is C. Okay, here in this case, the sum this integration of dq for the path B is equals to the integration of dq for the path C, and also the integration of dw for path B equals to integration of dw for path C. So we can conclude that the internal energy whatever path it may follow, so it is there will be no change in internal energy, hence the internal energy is a property of the system. So we have to prove like this. Next, Remember, the first law of thermodynamics gives rise to a new definition called as the internal energy. The internal energy is the net energy accumulated within the system, and it is neither the heat energy nor work energy. It is simply a form of energy represented by symbol either U or V. U or E. Similarly, the second law of thermodynamics gives rise to a new definition called as the entropy. Okay, entropy is also property represented by symbol S, and it is equals to the dq by t. Remember, so two formulas you should remember in first law of thermodynamics. Q equals to delta U plus W, and ds equals to dq by t in second law of thermodynamics. Okay, so first law of thermodynamics gives rise to a new definition called as the internal energy, and second law of thermodynamics gives rise to a new definition called as entropy. Okay, so one more concept that is called as perpetual motion machine of first kind. Okay, so this is the diagram. We have to show two diagrams. One is the engine. Here there will be extraction of the work, and you refer the first diagram. There will be extraction of the work energy from the engine, and there is no consumption of the heat. Okay, there is no heat transfer. That's why it is represented by symbol. And this is the dotted line. On the other hand, so we are having a machine. There will be only the supply of the work to the machine, but there will be no heat transfer from the machine. Okay, so whenever it is represented by dotted line, there is no heat transfer. Here also there is no heat input to the system. This is a dotted line, and continuous line is the exact amount of the work done is taken from the engine, and here continuous line represents the continuous consumption of the work to the machine. Okay. Okay, according to the concept, so it is impossible to construct the perpetual motion machine of first kind. Okay, so how it means perpetual machine is the one which perpetual motion machine is the one which can do continuous work. Okay, so without receiving the energy. Okay, uh, and violates the first law, because according to the first law of thermodynamics, the amount of work done equals to the amount of the heat transfer. If there is only one energy transfer is there, in that case it violates the first law of thermodynamics. Hence, the PMM one always violates the first law of thermodynamics, and it is impossible in nature. Remember, it's a perpetual motion machine of first kind. So you have to explain with these two diagrams. So in first diagram, you have to show a continuous extraction of the work from the engine without heat input to the engine. And in the second diagram, there will be continuous consumption of the work, so without the heat transfer from the system. Okay, because it violates the first law of thermodynamics. For first law of thermodynamics states that the total energy the associated with the system remains constant, and we can take the two mutually convertible forms of the energy. If only one energy transfer is there in the system, then it violates the first law of thermodynamics. Hence, the perpetual motion machine of first kind is impossible in nature, and it is a fictitious machine, and it violates the first law of thermodynamics. Okay, it is impossible to construct the perpetual motion machine of first kind. Now I'll do certain problems on first law of thermodynamics. Okay, simple problems. In a cyclic process, you see the heat transfer are plus 14.7 kilojoules minus 25.2 kilojoules minus 3.56 kilojoules and plus 31.5 kilojoules. What is the net work output for this cyclic process? Okay, so they are clearly mentioned the heat transfer. There are four heat transfer are there. Okay, one is plus and three 2R plus and 2R minus. Plus indicates the heat added to the system, and the minus sign indicates the heat rejected from the system. So according to the first law of thermodynamics, for a cyclic process, the cyclic integral of dq equals to the cyclic integral of dw. Okay, that is the net work done equals to. So first we have to do the summation of heat. That is plus 14.7, minus 25.2, minus 3.56, and plus 31 point. So we'll get uh, 17.44 kilojoules. So net heat transfer equals to 17.44 kilojoules. Okay, then we have to apply uh, the first law of the thermodynamics. In the problem, clearly mentioned it is cyclic process. In a cyclic process, summation of the heat transfer equals to summation of work transfer. Hence, whatever amount of heat transfer we are getting is exactly equals to the summation of work transfer. That is net work done equals to 17.44 kilojoules. Okay. You see the second problem. Consider a cyclic process in a closed system which includes three heat interactions, namely Q1 equals to 20 kilojoules, Q2 equals to minus 6 kilojoules, Q3 equals to minus 4 kilojoules, and two work interaction for which W1 equals to 4500 Newton meter. Newton meter is nothing but joule. Compute the magnitude of second work interaction W2 in Newton meter. So first, we have to write that is Q1 plus Q2 plus Q3 equals to the W1 plus W2. So in a cyclic process, the summation of work transfer equals to summation of heat transfer, that is Q1 plus Q2 equals to W1 plus W2. Okay. That is 20 minus 6 minus 4 equals to, that is kilojoules is that we have to convert into joules. That is 20,000 minus 6,000 minus 4,000 equals to 4,500 plus W2. So after solving this one, we are getting the W2 as 5,500 Newton meters. So we are applying simple formula, that is summation of the heat transfer equals to the summation of work transfer. You see the third problem. A domestic refrigerator is loaded with food and the door is closed. During a certain period, the machine consumes 1 kilowatt hour of energy and the internal energy of the system drops by 5,000 kilojoules. Find the net heat transfer for the system. So, solution is W1 to 2. That is the work done equals to 1 kilowatt hour. So 1 kilowatt hour means we have to convert into a second because multiply by 3,600. That is 60 into 60. That is minus 1 into 3,600 kilojoules. And U2 minus U1. Okay. So the change in internal energy drops by minus 5,000. Okay. So negative sign indicates the decrease in the internal energy, and the positive sign indicates the increase in the internal energy. So you have to write first the given data kilowatt hour. Don't put 1 as it is. That is 1 into 3,600. Okay, that is minus 3,600, and U2 minus U1 equals to minus 5,000 kilojoules from first law, and Q1 to 2 equals to you apply the first law of thermodynamics. So Q1 to 2 equals to delta U. Delta U is U2 minus U1. Okay, whenever the term comes delta U, you have to take the final internal energy minus initial internal energy plus W1 to 2. Okay, so just you apply the formula minus 5,000 minus 3,600 we are getting minus 8600 kilojoules. Here are minus 8.6 megajoules. Now you see, okay, sometimes they'll give the mm, tabular form like this. Okay. So you have to complete the data. Okay, so here for the following process in a closed system, find the missing data. Whatever the underline is there, no, there is the missing data. You have to fill that missing data. So there are five quantities for a process A. Q is 20, W is 20, U1 is minus 10, U2 not given, delta U is 15. Okay, for process A, the three quantities are given. One is W, one is U1 as minus 10 kilojoule, and delta U as 15. Our aim is to find out Q and U2 for the process A. Similarly, for the process B, Q is given 15 kilojoules, W is given minus 6 kilojoules. We have to find out U1, and U2 is minus 6 and delta U is we have to find out. Okay, similarly for the process C, Q is minus 7, W is 10, U1 is 20, and U2 we have to find out, delta U also you have to find out. And for the fourth process, D, Q is we have to find out, W is minus 7, U1 is 28, U2 is 8. Sorry, U1 you have to find out, U2 is 8, and delta U is minus 20. So you have to find out the missed out quantity. So you have to take all the process one by one. For the process A, Q equals to delta U plus W. So delta U is U2 minus U1 plus W1 to 2. So here in the problem, U2 minus U1, that is delta U is given 15. Okay, so you have to substitute the value. So U2, therefore U2 minus U1 is 15, U2 is 5 because U1 is given minus 10. So U1, U2 we are getting 5 and U1 is given minus 10. We have to apply this formula. U2 minus U1 equals to W1 to 2. U2 minus U1 is 15 or U2 is 5. You have to fill their data 5 and then you have to apply the formula. Q equals to delta U plus W, that is 15 plus 20 equals to 35 kilojoules. Similarly, you have to apply for the process D. Apply U2 minus U1 plus W. Then you have to write given quantities. Q is given 15 kilojoules. Okay, U2 is given minus 6 and U1 we have to find out, and W is also not given. Okay. So first we have to find out delta you have to find out. Okay, here only thing is given Q, W and U2. So Q is 15, U2 is minus 6 and minus U1 we don't know. W is 6 is given. So we have to find out U1 as minus 27 kilojoules. And delta U is U2 minus U1. Okay, U2 is given as the minus 6. Okay, U2 as minus 6 and U1 as minus 27. U2 minus U1 after substituting is minus of minus becomes plus. So we get delta U as 21 kilojoules. It's the second process. Similarly, you take the third process. Third process is delta U is Q equals to delta U plus W. Q is minus 7 and U2 minus U1. U1 is given 20 kilojoules. Okay. Plus 10. Plus 10 is our the work done. So unknown thing is U2. U2 is after substituting minus 7, U2 minus 20 plus 10, we are getting U2 as 3 kilojoules. And delta U is U2 minus U1. U2 is 3 kilojoules. U1 is minus 20. So we get 8 minus 20, 8 minus of minus 20 is 28 kilojoules. Okay. So like that, you have to apply the formula, simple formula, that is Q equals to delta U plus W. So you have to find out all the quantities. But simple formula, but only you have to remember the sign convention. Hope you understood this one. Okay, in first law of thermodynamics, they usually used to ask, give the statement for first law of thermodynamics, Joule's experiment to illustrate the first law of thermodynamics, and then what is the internal energy, the formula of internal energy, next perpetual motion machine of first kind, and the numerical problems related to that simple formula Q equals to delta U plus W. So I'll stop the session now. Those who have not entered your USN, please enter your USN in the chat box for attendance purpose. Once I stop the recording, you'll not get the attendance. Thank you guys for joining the session. Thank you.